Hello, I welcome you all. The problem reads if the cord is subjected to a constant force of F equal to 300 newtons and the 15 kg smooth collar starts from rest at A, determine the velocity of the collar when it reaches point B. Neglect the size of the pulley. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Benam. So we have a pulley here and it changes position from A to B. So as this happens, it means the rope will have also lengthened this side, right, where we have this force. So it means work is going to be done this side. And as the pulley moves from point A to point B, there is also going to be work done. So we need to account for this as we use the work and energy principle. Okay. Right. So let's draw what is happening. So let's say we do have this. Sorry. We use a straight line. Let's say we do have something like this. This is direction along which our force is going to move. So from that point to that point. Okay. Right. There we go. And then we have this point here. Okay. To this point there. Okay. This is the point where H itself, the collar will have reached. But we also have these other lengths that we need to account for, right? These lengths, as well as this one there from there to there, right? So all these lengths, we need to account for them. So let me just dot them. You don't have to do this. It's just my preference. Okay. Right. So now let's write what is really happening here. So we'll need to find this length from there to there. And once we found it, then we need to find another length from that point to there. Okay. Let me give it another color, that one. So let's call this one here as S, and let's call this one here as S star. Okay. And then we call this one here as S minus S star. Okay. So using the work and energy principle, we'll say the kinetic energy at A plus the total work done from A to B by the collar is just going to be equal to the final kinetic energy at B. And since the collar is starting from rest, this is going to be 0, like we said, because the collar starts from rest. Alright, so we do have 0 there plus the total work. We have the force, okay, times this displacement, and both are in the same direction. Force and the displacement are in the same direction. Hence, this is positive work. Okay. Then we do have minus W. Okay. This is WB times HB. Minus because the displacement is up while the force, the weight, is down. Okay. Therefore, we expect this to be negative work. Okay. So this is negative, like we said initially. So this is just going to be equal to, this is equal to the work, the velocity, the final kinetic energy for the collar as it reaches B. Okay. So S itself is just equal to point, this one here is 0.2 and this is 0.2, so this is 0.4 meters. This one here is HB, which is just equal to 0.3, 0.2, 0.5 meters. And this one here is 0.7 meters. Okay, so we have 0.7 plus 0.4. Okay, so here, there we go. And then we do have S star. This one is a 0.2, right? It's 0.2 by 0.2. Okay, like so. Okay, squared, and then the rest we know. So let's plug everything. So we have 300. We do have 300 meters. 300 newtons, sorry. And then can we copy this? I think we can. We copy this, we bring it there like so. Then we can also copy that, we bring that in, we bring it there like so. Bring it in advance. These are subtracting. There's a minus in between there. And we close this bracket. Then we say minus WB just 15 by 9.81. Then times the length, which is 0.5. Then equal to 1/2 times the mass times VB squared. VB therefore is just going to be equal to 0.7 squared plus 0.4 squared minus square root 0.2 squared plus 0.2 squared times 300 minus 15 by 9.81 by 0.5 divided by that, and then square root of that. So this just gives us a 3.34 meters per second. So this is the velocity of the column as it reaches point B. Alright, so I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing, liking my channel. Bye bye, and I'll see you in my next screencast.